Hello my dear students, once again welcome back to our class. Today I am going to explain about focal length of lenses in out of contact. Focal length of lenses in out of contact from the chapter Ray Optics. Right, Ray Optics, the chapter name and topic name is focal length of lenses in out of contact. Right. In the previous class, you learnt about focal length of lenses in contact. Focal length of lenses in contact. Right. In that topic, it was explained that when two thin lenses of focal length f1 and f2 brought in contact, when two thin lenses of focal lengths f1 and f2 are brought in contact, this combination is treated as a thin lens of focal length f. Right? In the previous class, it was explained explained about the focal length of a lens in contact. In that topic, it was explained that when two thin lenses of focal length f1 and f2 brought in contact, they are treated as a single thin lens. A single thin lens whose focal length is f. Whose focal length is f. The focal length of this effective focal length of the lens of this combination can be determined by using the formula 1 divided by f is equal to 1 divided by f1 plus 1 divided by f2. 1 by f is equal to 1 by f1 plus 1 divided by f2. Here f, effective focal length of a lens, f1 and f2 are the focal length of the individual lens. Focal length of the individual lens. From this equation, it is clear that the reciprocal of the reciprocal of the focal length of equivalent lens is equal to sum of the reciprocal of the focal length of the individual lenses. Sum of the reciprocal of the focal lengths of the individual lenses gives the reciprocal of the effective focal length. The reciprocal of the effective focal length. Right? Then its effective power is given by P is equal to P1 plus P2, where P power of this equivalent lens and P1 and P2 are the powers of the individual lens. Powers of the individual lens. Right? From this equation, it is clear that the effective power of the combination is equal to sum of the powers of the individual lenses. Sum of the powers of the individual lenses. Right? So these are the things we have to discuss in the previous class. And one more thing. When two thin lenses are brought in contact, the common optical center is chosen at the middle of the two lenses. So this is common optical center. Common optical center is chosen at the middle of the two thin lenses. And this combination is treated as a single thin lens. A single thin lens whose focal length is f, its focal length can be determined by using this relation, and its corresponding power can be determined by using the relation P is equal to P1 plus P2. But now we are going to discuss about focal length of lenses in out of contact. Focal length of lenses in out of contact. Right. Right. In this case, once again we consider two thin lenses of focal length and f1 and f2. And they are separated by a distance of d apart. Right? The topic name is focal length of lenses in out of contact. For that we consider two thin lenses whose focal lengths are f1 and f2. They are separated by a small distance apart. Suppose let it be d. Right. Now here the common optical center of this combination cannot be chosen. If the two thin lenses are separated by some small distance apart, the common optical center cannot be chosen for this case, right? And also, this combination cannot be treated as a single thin lens. Cannot be treated as single thin lens. When two thin lenses are brought in contact, the combination can be treated as a single thin lens. But if two lenses are separated by some distance apart, they cannot be treated as a single thin lens. But one special case is there. If the object is placed at infinity, if this combination can be treated as a single thin lens. Otherwise, they are treated as a thick lens. Treated as thick lens, right? If the combination is treated as a thick lens means it is very difficult to tell about the focal length of the combination and the position of the equivalent length. Position of the equivalent. So this is beyond the scope of your level. So for that, this combination is treated as a single thin lens when if the object is placed at infinity. Okay, otherwise this combination is treated as thick lens. Are you clear? If two thin lenses are separated by a distance of d apart, they cannot be treated as a single thin lens except only one case. That is, if the object is placed at infinity, this combination can be treated as a single thin lens. Otherwise, they are treated as a thick lens. Treated as a thick lens. Already I told, when two thin lenses are separated by some distance apart, that combination can be treated as a single thin lens only when the object is placed at infinity. When the object is placed at infinity, right? The focal length of the effective lens or new lens and the position of the new lens can be determined by using the concept of angle of deviation. By using the concept of angle of deviation, right? For that, let us consider a single converging lens or convex lens. Convex lens is also called a converging lens, right? And this is the principal axis of this lens. Principal axis. What is meant by principal axis? An imaginary line which is passing through the center of curvature and the optic center of a lens is known as principal axis. So this is principal axis of this lens, right? And the optic center of this lens is denoted by P, right? And there is a point object, suppose O, which is placed on the principal axis. Which is placed on the principal axis, right? A ray of light from this point object is incident on the lens at point A, right? Here P be the optic center of this convex lens and this line is called principal axis. On the principal axis we consider one point object. From the point object we consider one of the ray of light, that is OA, which is incident on the lens at point A. At point A, right? Here the line OA is called incident ray. Incident ray. This incident ray makes an angle of alpha with the principal axis. With the principal axis. So here alpha be the angle made by the incident ray with the principal axis. And this incident ray is incident on the convex lens at point A. At point A, right? So due to the refraction, this ray is deviated and strikes at point I on the principal axis, okay, where the image is formed, right? So due to the refraction, the ray is just deviated through an angle of, suppose a del, through an angle of del, and forms an image I on the principal axis, on the principal axis. So this is incident ray and this is called refracted ray. Refracted ray. So this incident ray deviated through an angle of del and forms an image of I on the principal axis. Here AI is called the refracted ray. This refracted ray makes an angle of beta with the principal axis. Right. Here incident ray makes an angle of alpha with the principal axis, whereas refracted ray makes an angle of beta with the principal axis. Right. Now consider this triangle O, A and I. So in this triangle, sum of these three angles, suppose this angle is taken as, suppose theta, right? Sum of these three angles is equal to 180 degree, right? So alpha plus beta plus this angle theta is equal to 180 degree. Right here, angle OA, suppose the distance of or the height of point of incident from the optic center of the lens is taken as H. Okay, here this incident ray is strikes on the convex lens at point A at a height of H from the optic center. Right. Here, this is alpha. That is the angle made by the incident ray with the principal axis is alpha. Okay, which is equal to AOP. So AOP is equal to alpha. Here refracted ray makes an angle of beta with the principal axis. That is angle AIP is equal to beta. So angle AIP is equal to beta. Angle AOP is equal to alpha. Here in this triangle, sum of these three angles is equal to 180 degree. So alpha plus beta plus theta is equal to 180 degree. Right. Here this angle is a theta and this angle is a del. So this is called angle of deviation. The purpose of angle of deviation introduced in this topic is that to determine the effective focal length of the combination of thin lenses, and also used to find the position of the equivalent lens, by using the concept of angle of deviation. Here this is called angle of deviation. It is denoted by del, right? So this angle is a del and this angle is theta. And this total angle is 180 degree. So del plus theta is equal to 180 degree. Del plus theta is equal to 180 degree. Right. Now comparing these two equations, theta common and 180 degree common. Here del is equal to alpha plus beta. So comparing these two equations, we can get del is equal to alpha plus beta. Right. We know that in mathematics one condition is there, that is if the given angle, that is the theta, is too small, then theta can be taken as tan theta. If a given angle, that is the theta, is too small, then theta is equal to tan theta, or tan theta can be taken as theta. Right? In this diagram, here height h is too small when we compare to this length PO and PA. Compared with PO and PI, here this height h is too small. If height h is small means then these three angles also small. So alpha, beta and del also are also too small. Right. If the given angle is so small, then theta can be taken as tan theta, or tan theta can be taken as theta. Here alpha, beta and del are also too small. So therefore alpha can be taken as tan alpha. Alpha can be taken as a tan alpha. Similarly, beta can be taken as a tan beta. Tan beta, right. Here consider this triangle, right angle triangle OAP. From the triangle OAP, right. So this angle is alpha. We need a tan alpha. So tan is nothing but opposite side by adjacent side. Here tan alpha is equal to opposite side PA. Tan alpha is equal to opposite side PA divided by adjacent side PO. Adjacent side PO. Right. Similarly, from the triangle IAP, this angle is beta. We need tan beta. So tan beta or tan is equal to opposite side by adjacent side. Opposite side PA and adjacent side PA. So tan beta is equal to PA divided by PI. PA divided by PA. Right. Substitute alpha value and beta value in this equation. Suppose this is equation number 1. Substitute alpha is equal to PA divided by PO and beta is equal to PA divided by PI in equation number 1. Right. So equation number 1 becomes del is equal to PA divided by PO plus PA divided by PI. Right. Here PA is equal to H and PO. So P is the principal axis and O is a point object. Point object. The distance between object and the optic center is called object distance. Object distance. By sign convention, all the distances measured from the left of the optic center should be taken as a negative. Here, this measurement is in left side of the origin, so that is why this object distance should be taken as negative, right? And all the distances measured from the right side of the origin should be taken as a positive. So here this is image position, this is principal axis, optic center. The distance between optic center and the position of the image is called image distance. Image distance is denoted by V. Image distance V and object distance U. By sign convention, object distance is a negative, whereas the image distance is positive. Right? Here Pi is equal to V and Po is equal to minus U. So substitute Po is equal to minus U and Pi is equal to V here. Then del is equal to Pa is equal to H. Po is equal to minus U plus Pa is equal to H and Pi is equal to V. So del is equal to H divided by minus U plus H divided by V. H divided by V, right? Or del is equal to H common, so take outside. So H of 1 divided by minus U plus 1 divided by V. Or otherwise del is equal to H of 1 divided by V minus 1 divided by U. Del is equal to H of 1 divided by V minus 1 divided by U, right? From lens formula, one divided by F is equal to 1 divided by V minus 1 divided by U. Lens formula 1 divided by F is equal to 1 divided by V minus 1 divided by U. Here, instead of 1 divided by V minus 1 divided by U, we can write 1 divided by F. Therefore, angle of deviation del is equal to H. Instead of 1 minus V minus 1 divided by V minus 1 divided by U, we can write 1 divided by F. So 1 divided by F, or del is equal to H divided by F. Del is equal to H divided by F. Right? From this equation, it is clear that the angle of deviation produced by the lens is equal to the ratio of the height of the point of incidence of the light on the lens to the focal length of the given lens. The ratio of height to the focal length gives angle of deviation. Height, the ratio of height to the focal length gives angle of deviation. So angle of deviation del is equal to H divided by F. So this is taken as equation number 2. Angle of deviation del is equal to H divided by F. It means angle of deviation is equal to ratio of height to the focal length. Height to the focal length. So far we derived the expression for angle of deviation. The obtained expression is del is equal to h divided by f. That is, angle of deviation is equal to the ratio of height to the focal length. The ratio of height to the focal length. Right. Now we consider two thin lenses of focal lengths f1 and f2. Okay, thin lenses of focal length f1 and f2. These two lenses are separated by a distance of d apart. The two lenses are separated by a distance of d apart. Right. The combination of these two lenses can be treated as a single thin lens if the object is placed at infinity. If the object is placed at infinity, the combination of these two lenses can be treated as a single thin lens. A single thin lens whose focal length is f. Whose focal length is f. Right? Here, this is one of the ray of light from the object. The object is where? At infinity. Okay? In that case only, the combination of two lenses can be treated as a single thin lens. Otherwise, they are treated as a thick lens. Right? Understand? If the object is placed at infinity, even the two lenses are separated by a distance of d apart, they are treated as a single thin lens. A single thin lens. Okay, if the object is placed other than infinity, that is other than infinity means before infinity, they cannot be treated as a single thin lens. Here the object is placed at infinity, so that is why this combination can be treated as a single thin lens whose focal length is taken as f. Whereas f1 and f2 are the focal length of the two individual lenses. They are separated by a distance of d apart. Separated by a distance of d apart. Right. Here P1 and P2 are the optic center of first lens and optic center of second lens. Right. If two lenses are separated by some distance apart, the optic center, common optic center cannot be chosen. Okay, common optic center cannot be chosen. Suppose if the two lenses are brought in contact, there is a common optic center is chosen at the middle of the two lenses. But for this case, the common optic center cannot be chosen. So that is why here P1 and P2 are the optic center of first lens and optic center of second lens. And P is the optic center of the new lens. The optic center of new lens. New lens means equivalent lens. Equivalent lens. Right. Here, the ray of light from the object which is at infinity is incident on the first lens. Where? At point B. At point B. It is deviated by this first prism by an angle of del 1. Right? And which is incident on the second lens at point C. And this ray is deviated by second lens by an angle of or through an angle of del 2. So del 1 and del 2 are the angle of deviation produced by the first lens and second lens. The angle of deviation produced by the first lens and second lens. Here the light from the object which is at infinity is incident on the first lens at point B at a height of h1 from the optic center P1. This refractor ray is incident on the second lens at point C at a height of h2 from the optic center P2. And the angle of deviation produced by the second lens is del 2. So the total angle of deviation produced by these two lenses is given by total angle of deviation. Total angle of deviation produced by the combination of two lenses is, suppose del, which is equal to del 1 plus del 2. So del 1 angle of deviation produced by the first lens and del 2 angle of deviation produced by the second lens. So total angle of deviation produced by these two lenses is equal to del, which is equal to del 1 plus del 2. Okay, so total angle of deviation produced by the new lens is del, which is equal to sum of del 1 and del 2. So total angle of deviation is del is equal to del 1 plus del 2. Suppose this is taken as equation number 1. So what is there? The total angle of deviation produced by the combination of two lenses, which is equal to del 1 plus del 2. Del 1 angle of deviation produced by the first lens and del 2 angle of deviation produced by the second lens. Right. Already we know that angle of deviation is nothing but the ratio of height to the focal length. The ratio of height to the focal length is nothing but angle of deviation. Right, here the total angle of deviation produced by the combination of two lenses is a del, which is equal to del 1 plus del 2. Here del 1 is equal to h1 divided by f1. Del 1 is equal to h1 divided by f1. Because height is h1 and focal length of the first lens is f1. And the ratio of height to the focal length gives angle of deviation. So angle of deviation del 1 is equal to h1 divided by f1. Similarly, here height is h2 and its focal length is f2. The angle of deviation produced by the second lens del 2 is equal to h2 divided by f2. Similarly, del 2 is equal to h2 divided by f2. h2 divided by f2. Therefore, total angle of deviation is del is equal to h1 divided by f1 plus h2 divided by f2. Del is equal to h1 divided by f1 plus h2 divided by f2. h2 divided by f2. Right. So this is taken as equation number 2. Now see the diagram. So in this diagram, so this length is P to G. Here P to G is equal to PE and PE is equal to P1B. P1B is equal to H1, right? Here P to G is equal to P to G is equal to H1, right? Here this length P to C is equal to H2. So from this diagram, P to G is equal to H1 and P to C is equal to H2. Right. Suppose if you want to calculate CG value means just you subtract P to G from subtract P to C from P to G. Suppose we need CG. CG is equal to P to G minus P to C. CG is equal to P to G minus P to C. Right, CG value. Right, here CG is equal to P to G is equal to H1 and P to C is equal to H2. So CG is equal to H1 minus H2. CG is equal to H1 minus H2. Right. Okay, now we consider one right angle triangle in this diagram, that is B, G and B2. Sorry, B, G, C. Right. So from the right angle triangle BGC, from the right angle triangle BGC, so this angle is del 1. This angle is del 1. Right, here del 1 is too small. Not only del 1, del 1 and del 2. These three values are too small because here height H1 is too small as we compared to P1, P2, P1, P2 or P1P and P2. So if height is too small, then the corresponding angles also small. So del 1, del 2 and del are too small. Here del 1, del 2 and del are too small. Already I told, if a given angle is too small, the angle that is theta can be taken as tan theta. Theta can be taken as tan theta. Here del 1 is too small, therefore del 1 can be taken as tan del 1. Tan del 1. Right. In this right angle triangle BGC, this angle is del 1, but we need tan del 1. So tan theta is equal to opposite side by adjacent side. Opposite side by adjacent side is nothing but tan. So tan del 1 is equal to opposite side CG divided by adjacent side BG. Adjacent side BG. Right. So therefore we need CG. So CG is equal to BG into tan del 1. CG is equal to BG into tan del 1. Here BG is equal to D. What is D? The separation between two thin lenses. Separation between two thin lenses. Therefore, CG is equal to, instead of BG, D. And already I told, if theta is too small, tan theta can be taken as theta. Here del 1 is too small, therefore tan del 1 can be taken as del 1. So CG is equal to D into del 1. Right. Now substitute here. CG is equal to H1 minus H2. Substitute GG value here. So therefore, suppose this is equation number 3 and this is equation number 4. Now compare equation number 3 and 4. Therefore, H1 minus H2 is equal to CG is equal to H1 minus H2. So instead of CG, H1 minus H2, which is equal to D into del 1. Right. Therefore, H2 is equal to H1 minus D into del 1. H2 is equal to H1 minus D into del 1. Right. H2 is equal to H1 minus D. Here del 1 is equal to H1 divided by EF1. So del 1 is equal to H1 divided by EF1. Here H1 common, so take outside. Therefore, H2 is equal to H1 of 1 minus D divided by EF1. Right. So this is taken as equation number 5. So H2 is equal to H1 of 1, H1 common, so take outside. So H1 of 1 minus D divided by F1. So this is taken as equation number 5. Right. Now substitute H2 value in equation number 2. Okay, instead of H2 we can write H1 of 1 minus D divided by F1. So substitute H2 value here. Here del is equal to H1 divided by F1 plus H2 is equal to H1 of 1 minus D divided by F1 divided by F2. H2 is equal to H1 of 1 minus D divided by F1 divided by F2. Right. So del is equal to H1 divided by F1 plus H1, just to take H1 inside. So H1 minus D H1 divided by F1 whole divided by F2. Right. This equation becomes del is equal to H1 divided by F1 plus H1 divided by F2 minus D H1 divided by F1 into F2. Right. So this equation can also be written as del is equal to H1 divided by F1 plus H1 divided by F2 minus D H1 divided by F1 into F2. Right. Already I told here del is equal to, what is del? The total angle of deviation produced by this combination, or the total angle of deviation produced by the new lens. Here this is angle of deviation produced by the new lens. Height H1, its focal length is F. Therefore angle of deviation is nothing but height, the ratio of height to the focal length. So angle of deviation del is equal to height H1 and its focal length is F. Right. Now substitute del is equal to H1 divided by F in this equation. Suppose this is equation number 6. Right. Now equation number 6 becomes H1 divided by F is equal to H1 divided by F1 plus H1 divided by F2 minus DH1 divided by DH1 divided by F1 into F2. Right. Therefore H1 divided by F is equal to, here H1 common, so take outside. So H1 of 1 divided by F1 plus 1 divided by F2 minus D divided by F1 into F2. Here H1 get cancelled. Then 1 divided by F is equal to 1 by f1 plus 1 by f2 minus d divided by f1 into f2. f1 into f2. So this equation gives the focal length of a new lens. The focal length of a new lens. That is the effective focal length of a combination of two thin lenses having focal length f1 and f2. F2 can be treated as a single thin lens when the object is placed at infinity. Its focal length is f. That value can be calculated by using the formula 1 divided by f is equal to 1 by f1 plus 1 by f2 minus d divided by f1 into f2. Here f1 and f2 are the focal length of the two thin lenses, and d the separation between the two lenses. Separation between the two lenses. If you know the focal length of the two lenses and the separation between the two thin lenses, we can determine the focal length of the effective lens. The focal length of the effective lens or focal length of the new lens. Okay, it is given by relation 1 divided by f is equal to 1 by f1 plus 1 by f2 minus d divided by f1 into f2. D divided by f1 into f2. Right, now listen the diagram. Here, this P is nothing but the optic center of a new lens, and P2 is the optic center of a second lens. Optic center of second lens. Right. Here, the distance of P2 is equal to EG. Here, P2 is equal to EG. So this distance are equal. So that is why I am right, P2 is equal to EG. Right. Now consider this right angle triangle. Okay, from the right angle triangle EGC, this angle is a del. So therefore tan del is equal to opposite side CG divided by adjacent side EG. Adjacent side EG. Right. Here EG is nothing but P2. Right. Therefore tan del is equal to CG divided by EG is nothing but P2. Therefore P2 is equal to CG already derived. CG is equal to H1 minus H2, or CG is equal to D H1 divided by F1. CG is equal to D H1 divided by F1. Already we derived CG equal to H1 divided by H1 minus H2, or CG is equal to D H1 divided by F1. Right. Substitute CG is equal to D H1 divided by F1 here. So D H1 divided by F1 divided by tan del. Tan del. Right. Here del is too small, therefore tan del can be taken as del. Tan del is taken as del. Right. Therefore P2 is equal to D H1 divided by F1. Instead of tan del, we can write del. So P2 is equal to D H1 divided by F1 into del. F1 into del. Right. Already I told del is equal to H1 divided by F. Okay. Here total angle of deviation produced by the new lens is equal to the ratio of height to the focal length. So del is equal to H1 divided by F. Del is equal to H1 divided by F. Therefore, so H1 divided by F can be written as del. Right. So P2 is equal to, instead of H1 divided by del is equal to H1 divided by F. Therefore F is equal to H1 divided by del. So instead of H1 divided by del, we can write F. So P2 is equal to D divided by F1. Instead of H1 divided by del, F. Right. So this equation gives the position of a new lens, or position of equivalent lens from the second lens. So what is the distance of the new lens from the second lens? P2. So the position of the new lens the position of the new lens from the second lens can be determined by using the formula P2 is equal to DF divided by F1. What is a D? the total distance between the first lens and the second lens. F, the focal length or effective focal length of the new lens or the focal length of the new lens. And F1, the focal length of the first lens. If you know the focal length of the first lens and the focal length of the new lens and the separation between the two thin lenses, we can calculate the position of the new lens from the second lens. The position of the new lens from the second lens. Right. Similarly, the distance of the position of the new lens from the first lens is P1. The position of the new lens from the first lens is P1. How can you calculate the position of the new lens from the first lens? By subtracting the P2 value from D, we can get the position of the new lens from the first lens. So the position of the new lens from the first lens is P1, which is equal to D minus P2. D minus P2. So subtract P2 from D, we can get P1 P or P1. Right, P1 is equal to D minus P2. Right. So D minus P2 is equal to D F divided by F1. D minus P2 is equal to DF divided by F1. So D common, so take outside. Therefore, P1 is equal to D of 1 minus F divided by F1. So this equation gives the position of new lens from the first lens. The position of new lens from the first lens is given by P1 is equal to D of 1 minus F divided by F1. The position of the new lens from the second lens is given by P2 is equal to DF divided by F1. Right. And the effective focal length of the new lens is given by 1 divided by F is equal to 1 divided by F1 plus 1 divided by F2 minus D divided by F1 into F2. Already I told the focal length and the position of the new lens, that is equivalent lens, can be determined or can be derived. The expression can be derived with the help of a concept of angle of deviation. Here the equation P2 is equal to DF divided by F1, P1 is equal to D of 1 minus F divided by F1. 1 divided by F is equal to 1 by F1 plus 1 by F2 minus D divided by F1 F2. These equations are derived with the help of a concept of angle of deviation. Concept of angle of deviation. What is concept of angle of deviation? Angle of deviation is nothing but the ratio of height to the focal length. The ratio of height to the focal length. Right. So once again, I explained from the beginning, when two thin lenses are separated by some small distance apart, they can be treated as a single thin lens only one case, that is when the object is at infinity, okay, whose focal length can be determined by using the formula 1 divided by F is equal to 1 by F1 plus 1 by F2 minus D divided by F1 and F2. Definitely that single thin lens, that is imaginary thin lens, should be lie in between these two lenses. The position of the new lens from the second lens from the first lens can be calculated by using the formula P2 is equal to DF divided by F1 and P1 is equal to D of 1 minus F divided by F1. So this equation gives the position of the new lens, that is equivalent lens, from the first lens. And this equation gives the position of the new lens from the second lens. And the effective focal length of the new lens can be calculated by using the formula 1 by F equal to 1 by F1 plus 1 by F2 minus D divided by F1 into F2. So these three equations are derived with the help of concept of angle of deviation. Right. Okay, thank you student. The focal length of lenses in out of contact topic is over. If you have any doubt, you call me or send message to my WhatsApp number. Right. Thank you student. We will see in the next class.